And welcome everybody. Good afternoon. I am Mike Matzura. I'm our business unit manager for North America, and I manage our Radiant group. Just 2 seconds about me. I am an engineer by background, and my entire career has been focused around low temperature heating and cooling systems with a specialty in radiant cooling. So I'm going to dive right into it. I'm going to turn my camera off here so you don't have to look at me, and then we're going to get into it because we got a lot to cover. So I'm going to take my 30-second commercial break here. Zehnder Rittling is based out of North America. Our headquarters is Buffalo, New York. Some of you may recognize the name Rittling. We do manufacture other product, specifically wet heat, hydronic wet heat, cabs, convectors, unit heaters, panel radiators, things of that nature. But all the product that we're going to talk about later is produced out of this Buffalo, New York facility. It's a lovely place to visit during the summer. During the winter, it's a little bit colder, but we do utilize all of our radiant technology in this space on the manufacturing floor and also do radiant cooling in the office itself. Zehnder Group acquired us in 2006. We are a global company. We have 22 other manufacturing facilities throughout the world, and our core competency is really radiant. In 1956, we released and started the design, well, actually, excuse me, we started the design in 56, but released our first product in 1958 on the radiant side, and that was called the ZBN product. And to date, we still manufacture this and is still our #1 moving product globally. So I tell you these things because I want you to realize that it's not Mike out of his garage building this product. That we as a company have a long-standing history. We have a lot of experience when it comes to not only the panel design, but the system design, the approach itself. So let's get right into it. Advantages of radiant systems. Why would we want to use a radiant system, whether it's heating or cooling? Well, generally, it's going to be more efficient. And when you look at these as design engineers, I want you to think of this as a tool for your toolbox. Right? Radiant is going to be another tool that you can utilize into your design. When you take that holistic approach towards your building and you're trying to build a energy efficient system for the commercial space, this is just another tool, right? Energy or water holds more energy per unit volume, and it's cheaper to move it from point A to point B than air and fans, right? When we're talking about water temperatures, we're talking about higher or lower heating temperatures. Generally, I'm not looking for 180-degree hot water temperature to do your heating. Generally, I'm looking for something around 120 to 140. Same thing on the cooling side. Typically, most systems, we're not looking for 42 or 45-degree water. Typically, I see somewhere between 55 to say 60 degrees. In general, most of the commercial spaces that we see the base building being built from cold compliant with the cold compliant commercial space and the mechanical systems. Then we see the base building where the next building being built with all the energy efficiency into it. Those typically I see somewhere between 25 to 35% energy savings over that. And that's taking, again, a holistic approach looking at the entire mechanical system. One of the things that we've been seeing more and more of over the years has been this conversation about thermal comfort. And it's really come to the forefront over the years of being more important when we talk about commercial designs and how comfortable people are within the space. When we talk about radiant, we're not talking about moving mechanical equipment. We're not talking about fan coils. We're not talking about motors being in the space. So the system themselves are extremely quiet. I don't like to simplify it too much, but we're talking about water coming in and water going out. So there's no moving parts. And from a maintenance and operational point of view, there's no fans, there's no filters, there's nothing that really needs to be replaced. And there's nothing in the space that needs to get touched with regards to the radiant itself. Architecturally, I see a lot of our industry changing, or I've seen the industry change, excuse me. I've seen the industry change over the years. From an educational point of view, we do a lot of K through 12 installations, and a lot of those older retrofit applications, we saw wall fin radiators, high temp heating. A lot of those installations are making a change to using radiant ceiling panels to deal with that perimeter heating load instead of using the wall fan. K through 12 has been popular because, and especially in those younger generation, younger years, you see a lot of those kids, whether they're melting gum on the element or kicking or denting the enclosure itself, and then the facilities engineers have to, over the years, paint it, replace it, or change it. The enclosure is hanging half off the wall. So again, getting it off the wall, putting it in the ceiling is a nice solution just to deal with your perimeter load. And then you can utilize another commercial or another HVAC system on the inside of the space to deal with your heating and cooling, whether it's VRF or a box or some other needs. So I get a lot of questions about applications. What are the best applications for a radiant system? I've seen just about everything over my career. I would say over the past number of years, some of the more popular applications have been higher education, universities, office buildings prior to COVID were very popular, open commercial spaces. Airports have really picked up. I would say a lot of the airports throughout North America are now utilizing the radiant cooling and heating system. Even if that airport is not utilizing the cooling and heating within the, say, the boarding areas or the interior core past the security, a lot of the airports are now using just the perimeter and using panels along that large glass facade to deal with that load. So healthcare is another popular application for us in the vertical market. I've seen hospitals, I've also seen laboratories themselves, and a lot of municipal buildings too. All right, so this is the worst part of the presentation, and I apologize. I'm going to try to make this as painless and quick as possible, but I want to make sure that we're all on the same page moving forward throughout this presentation. We are talking about the exchange of energy from object to object without heating or cooling the air. So we are talking about radiation. We're not talking about conduction, where two objects have to touch each other to allow that heat exchange. We're talking about radiation. Again, not convection, where we're allowing hot air or allowing air and buoyancy to pass over a conditioned coil. This is the exchange from object to object without heating or cooling the air. And it's very, very important that we remember this as we move forward. All right, so radiant heating, and don't get hung up on the water temperature so much. I really want to just simplify this. So as your hot water comes into your conditioned surface, the surface itself becomes heated. It gives off electromagnetic waves. It then turns and hits the objects themselves. Those objects in turn then heat the air. What I didn't say, and I want to point this out, what I didn't say was the controlled surface heats the air and then heats the occupants. It's very, very important to remember this as we move forward, because I'm going to talk a little bit about ASHRAE 55 and thermal comfort and what that means. So I get a lot of questions on the cooling side. I get a lot of questions on the cooling side of how that works too. So generally you see 56, again, don't get hung up on the water temperatures. You see chilled water, cold water coming into your control surface. The objects in the space then give off radiation. Now, in cooling mode, there are two modes of heat transfer. There's radiant and then there's the convective. But the radiant part, all the objects are giving off electromagnetic waves. They're being absorbed into that controlled surface, that chilled ceiling. And then the second mode of heat transfer is convection. So naturally, hot air rises to the ceiling. It rolls across the face of the panel, and then it comes back down. When you break it down between the two, looking at heating and cooling mode, heating is generally about 100% radiation. On the cooling side, it's generally 70-30. 70% of the heat exchange or the energy exchange is radiation. The other side of it, 30%, is generally convection. This is a general rule of thumb. Again, I just wanted to give you an idea of how that energy exchange occurs. All right, so as designers, when we approach a building, you have to take into account the 6 factors per ASHRAE standard 55 and the comfort that occupants feel in that space. 2 of the 6 we can't control, but the other 4 we can. And why is it important for us to focus on air temperature and radiant temperature, air velocity, humidity? Because that's what drives people comfort. And when we talk about radiant in general, we have to have this conversation about ASHRAE 55 and operative temperature. Well, what is operative temperature? In a radiant-based system, operative temperature is the actual temperature occupants will feel in the space. And I get a lot of questions about this because it always goes back to, well, Mike, isn't that just the air temperature in the space? No, it's not. What we found, and through the years and years of installations and measurements, is specifically in this case, in this example, what I'm showing here is what the air temperature being is 65 in heating mode, the surface temperatures are being 75, your actual perceived temperature is 70. So what that means is when we manufacturers design radiant-based systems, in heating mode, we will design an air temperature somewhere between 65 to 68. And in cooling mode, we will design somewhere between 76 to 78. And then generally, based on the mean radiant temperature, the amount of active surface area you have versus uncontrolled surface area, you will generally find it somewhere between 3 to 4 degrees lower or higher than that. So there's an inherent savings built into that right off the bat because you're designing at a higher or lower set point, but you're also delivering a very comfortable space for your occupants. I encourage any of you, if you get the chance to walk through a radiant cooled application, take a temperature reader with you or something with you with the manufacturer, and you'll notice that that air temperature is going to be higher in cooling mode than what you actually perceive. There are a number of tools out on the market that you can utilize because I'm not going to lie, it's quite a long calculation to come up with your operative temperature because it's a weighted average of all your controlled surface temperatures versus your uncontrolled surface temperatures. And generally, we all don't have time to make those calculations per space. So like I said, there's a number of tools out there, this being one, an operative temperature tool graph, that you can calculate your mean radiant temperature versus your dry bulb, and then come up with what we call as a T operative or your TOP, your operative temperature the occupants will actually feel. California Berkeley also developed a tool that's online and available to everybody. I don't want to get into, and I'm not going to get into a lot of the detail on this, but it's a free tool out there that was sponsored by TC 6.5 and ASHRAE. And you could input your mean radiant temperature, your air velocity, operative temperatures. There's a number of factors in here that you can change over to determine whether you are compliant with ASHRAE 55. It's a very, very powerful tool when looking at not just radiant systems, but other systems too. So that's another reference out there for everybody. All right, so what do these spaces generally look like? And I have thermographic images of heating and also cooling mode. And this was a service train station that on the left-hand side of the building, it was the all air system. And you can see where the heat distribution ended up, all at the top of the ceiling. Heat rises, we're not changing the principles of thermodynamics. And what do we do as designers now? We have to figure out a solution to get that hot air down to the lower area where all those occupants are and where they're working. On the other side of the building, on the other side of the wall, excuse me, we did a radiant system. You can see in heating mode how all those objects in the space absorb the energy and then emit it back into the space. So I get a lot of questions of why is radiant so comfortable? The reason radiant is so comfortable is because you're minimizing the surface temperatures between the uncontrolled surfaces and the occupants. I think we can all relate to standing next to a cold window during the winter. If that glass surface temperature is extremely cold and you're standing next to it as the occupant, that delta T between the surface of the glass and you as the occupant is very large. And the bigger the delta T, the more energy that gets sucked out of you as the occupant, which creates a level of discomfort. So by minimizing those delta T's, you create a high level of comfort for the occupant. Looking down the center, between the left-hand side image, where is the all air-based system, and then the right-hand side, where is the radiant system, you can really start seeing a difference between why the radiant system would be more comfortable versus the air system. I have an IR image here of a radiant cooled system, and it's not as impressive as it is in heating mode, unfortunately, but I wanted to show everybody here so you can see what it looks like as far as, again, we're trying to minimize those delta T's between the occupants and the uncontrolled surfaces. And that's what, at the end of the day, is really driving everyone's comfort. All right, so let's talk a little bit about design criteria, what the approach is when we're looking at these systems, and a little bit more detail on how we would design them. So generally, hot water systems, somewhere between 90 to 200 degree water on the entering side, chilled water side, somewhere between 54 and 63. What will drive your entering chilled water will be your dew point, and we'll talk a little bit more about that when we talk about controls and piping. So 54 to 63 on the chilled water side. On the heating side, generally, you don't want to go above 200 degrees on your surface temperatures. Now, the first question I get all the time is, Mike, do you want to put 180 degree water through an 8 or 10 foot mounted panel? Absolutely not, because the intensity is going to be so high that you're actually going to create a level of discomfort for the occupant. So ASHRAE and the committees have determined and come up with standards that basically says, depending on the mounting height of the panel, depending on how much active surface area is within the ceiling space itself, will drive what your average surface temperature should be, so you don't create a level of discomfort for occupants. I believe at a 9-foot mounted ceiling with 40% active coverage, you're looking at something like 140 degree water as your max, and that would not create a level of discomfort. So basically the intensity would be low enough that occupants wouldn't feel that a hothead. On the cooling side, generally we're looking for somewhere around 62 degrees on the colder side. And what do those numbers, those surface temperatures correlate to? They're very important to us as designers because they correlate to BTUs per square foot. On the heating side, up to 300 BTUs per square foot with a 10 to 30 degree differential delta T across the circuit or panel, depending on the panel size. On the cooling side, somewhere between 35 to 60 BTUs per square foot with a delta T of somewhere between 5 and 10. So the next question becomes, well, could you have given me a wider range on the cooling side from 35 to 60? And the response of that is, well, it depends. And the reason it depends is it depends on how these panels are installed. If the panels are installed in a closed ceiling like this, like a standard lay-in grid application, that is going to be one performance. If they have insulation on the back, that would then generate a second performance or different performance. If these are open to structure with or without insulation, that will generate a second or third different kind of performance. So where I'm going with this is it's important to understand what you're integrating these panels into, because that will drive the BTUs per square foot of the panel. One of the pitfalls that I've seen happen over and over again on schedules and drawings has been the initial selection being with either a closed ceiling or a open to structure capacity in cooling or heating mode, and then the design is switched to the opposite, and you don't get that same BTUs per square foot. So then you have to either add more square footage in, change some water temperatures, or change panel types to make sure that you're covering your load. So just something to be aware of when you're approaching the design. With regards to the panels, these are lightweight, fast reacting panels. So generally we design 1 to 2 degrees supply water temperature above your dew point to avoid condensation. I designed a lot of high mass systems, meaning in slab PEX tubing. Generally, you would design those a little bit higher, somewhere between 4 to 5, because they're utilizing the building mass as the condition, your active surface area, and they take a little bit longer to react. These being lightweight, fast reacting panels, they dissipate their energy very quickly. So you can design a little bit closer to your dew point and get more BTUs per square foot out of them. And then thus getting more BTUs per square foot, you could utilize less active area. That's not to say you have to design 1 to 2 above the dew point. I've seen many applications 3 to 4. It's really your level of comfort at that point, and also in the design, your understanding of the system and how you feel and the customer that you're dealing with feels about it too. All right, so we've talked a little bit about the performance. It's important that we now talk about how panels are tested. So about 35 years ago globally, when the industry really started, there was no standard of testing. So our industry again, globally looked at and said, what's the closest thing out there that we can utilize to test a radiant ceiling panel? Well, overall, there were wall panel radiators on the market. And there was already a standard developed for these wall panel radiators, which was 3528, which was the first one. It's now called EN442. But if you read the specification for it, it is actually a specification for convective type space heaters. So what happened a number of years ago was, as radiant manufacturers globally started releasing product into the market, they went out and saw that there's no standard testing. They said, oh, wow, hey, we have these EN442 labs already approved. Let's just stick it on the wall and measure the performance of the radiant panel. Well, what are you measuring? You're measuring a panel radiator at that point. And what happens is, when you take that ceiling panel and you put it on the wall, you get output somewhere near 80% convective, 20% radiation. And then when you change the configuration and put it in the ceiling, you get 70% radiation, 30% convective. So by changing the orientation in the space, you're changing how that panel performs. So over about 15 years ago, the industry came together and said, enough is enough. We need to develop standards that create a benchmark and standard for everybody, all radiant manufacturers. And we developed two standards, one for heating and one for cooling. And these standards clearly define not only the lab, but where the globe sensors go, how the panels are installed, the active area, the mounting heights. Every parameter is defined in these standards to make sure that when you compare as a designer performance from one manufacturer to another, you're comparing apples to apples, and you're not getting, I'll say, quote unquote, in-house testing or tested in accordance with. This creates that benchmark, and it's similar to AHRI when you test coils or anything else like that, other mechanical equipment. In 2013, ASHRAE 6.5, the committee, we passed ASHRAE 138, which we took and used as the benchmark of the EN standards for cooling and heating, and we revised them and rewrote them to fit our market. So either or will work. They're both measurements for rating sensible only heating and cooling panels when you write your specifications, and you know as a designer that you're using the actual performance that's measured in a lab, third-party tested according to the standard. So it's very important. So now, when you come to a manufacturer, or at least when you come to us, I'll say it that way, you ask us for performance, we're going to give you the performance based upon the standard. So if the standard produces, and I'm just going to pick a number, 35 BTUs per square foot based on your design conditions, that is what we're going to size the system, the active area on. That'll be the number that we would use. Now, over the years, and through the installations and through modeling and verification in the field, we have come to the conclusion, and we know that there are 6 other factors, and I'm not going to go through all of them. I just pulled 2 of them out here to go through them just to give you an idea, but there are 6 other factors that happen in the field that will actually drive up your performance during certain times of the installation or during certain times of the day. For an example, asymmetric radiation. We know that during direct solar sunlight time, you're going to get light that passes through the glass, through the facade, and start warming up certain areas within the space itself. So if you have a large glass facade, when that sunlight, that direct solar sunlight, comes into the space, warms up the floor, the windowsill, the occupant, or the table, what's happening? You're driving up that surface temperature on that object, and you still have the chilled surface. And now as that chilled surface temperature stays the same, let's just call it 60, and this temperature starts going up, the delta T between these two surfaces increases. As that delta T increases, you get more BTUs per square foot. Now, we all know the sun moves, so as the sun changes and moves, you lose that solar radiation, you lose the delta T, but I like to point these things out because as a design engineer, you size the system based on the capacity from the standard, but you know that you're going to get, quote unquote, a safety factor because you're going to have asymmetric radiation in this example for installations. The other one of the other sides of this is air outlet integration. I'll see a lot of diffusers, or even more popular nowadays, I've seen a number of installations has been ceiling fans. And mounting those fans and creating a convective flow below the ceiling panels themselves increases that convective factor across the panels. Now you're not derating them, you're actually just adding additional capacity to them. So you're adding that extra capacity, so you now have, again, another safety factor, knowing that you're going to get that in the actual space itself. Manufacturers can tell you what these values are depending on, feet per second or velocity of the air. They'd be able to give you the percentage increase over the base, meaning the base output capacity that's generated from the standard. We can tell you what those are going to be, so you'll have a general idea. Moving through the system or moving through your design, you'll have an idea of what that safety factor looks like. I also have seen over the years, as you become more experienced with the radiant system and you've done a number of them, I've seen engineers actually reduce the number of active panels in the space using these factors, which then, of course, reduces your overall installation cost too. All right, so let's talk about spacing and optimization. When we talk about covering a lot of the edge ceiling space, whether it's 30, 40, 50, 60% of the coverage of the ceiling, we have to have this conversation about spacing, distribution, and creating a comfortable environment for the occupants, right? Because we don't want to create spots where you would be uncomfortable, too hot or too cold. General rule of thumb that I give everybody that simplifies this approach is take the height of the panel that you're mounting off the floor, and that is generally your spacing from center line to center line of the panel. So if you're mounting the panels at 9 feet, 9-foot spacing from center to center is your maximum. Now, if you have more panels that take up more ceiling space, putting them closer is not a problem, but that's really the maximum distance you want to watch. The next question I get is off the perimeter walls. Where do I mount that first panel off the wall? Take your ceiling height, or excuse me, the height to the panel, divide it by 4, and that's going to be the distance from your facade to the center of the panel. And that'll give you the spacing, so you have proper spacing and proper coverage along the perimeter too. All right, piping and controls. So I pulled 2 examples that I see in the industry or see most of the time being utilized to control these systems. There's a number of different ways to do this, but these are probably the two most popular designs I've seen. So in this application, I have a 4-pipe system. I have a cooling only circuit, and I have a heating cooling circuit. This can be a single zone. So you could have cooling only panels on the interior core space, and then heating and cooling panels along the perimeter, or these can be 2 separate zones completely, 2 separate rooms. So there's a couple different ways of looking at it, but generally your chilled water system, chilled water pipe would open, your 2-way valve would open, would pass through into your cooling loop or your cooling circuit, and then returns through your 3-way valve back into the return side. And in this case, I actually have a secondary flow here that allows the chilled water into my cooling only loop, and then passes back into and mixes in with that return from the other circuits. When we switch over to heating, same thing happens. 2-way control valve opens up on the hot water supply side, goes through my heating only circuit, and then the 3-way valve diverts it back into my hot water loop. And then in this case, I would have no hot water passing through the cooling only circuits. So that's one of the popular options I've seen over the years. The other one is utilizing 6-way valves. So in this example, you have your chilled water entering your 6-way valve and then going out to your loops. Now on the right-hand side, I've got a couple different ways of piping the panels, so I don't want to focus too much on this, just on the actual piping itself. I'm going to talk more about options and piping and things of that nature later. So your 6-way valve will divert and allow your chilled water into your circuit, and then returns back into your chilled water return. On the heating side, the 6-way valve does the same thing, opens up and diverts into your circuit, and then returns your hot water side, hot water back into your return water pipe. So like I said, there are a number of different ways to achieve this. Injection pumping is another one that I've seen over the years, but these tend to be the two prominent designs that overall. So let's talk a little bit about what's on the market, and let's talk about why you would use what panel versus what and where. We divide the market into two separate segments, an economical and an engineered. On the economical side, we see perimeter linear panels and modular panels. I'm pretty sure that most of you are familiar with probably both of these and used either one of these and or both in applications. I'll go through each one. Linear panels, these are linear extruded panels. They come in different widths, in 4 foot, 5 foot, 6 foot. Manufacturers offer different widths depending on each manufacturer. Typically, standard is aluminum construction with aluminum saddle, and then the copper tube is fastened in that saddle on the back. These typically come with factory shipped loose U-bends and interconnects. So that's something to be aware of as a designer, what you're specifying. Something also to be aware of, these are typically used for heating only applications. And I see a lot of these installed, again, along perimeters where you're dealing with just the heating load separated from the interior core space. And that could be either a 12, 24, or 36 inch width wide panel just to handle that heating side. Things to be aware of and pitfalls. These are copper aluminum panels. So depending on what your water temperatures are, depending on what your steady state is, as if you were to hit this with hot water, say 180 degrees or 200 degree water, that copper tube inside will expand and contract. And as it expands and contracts, it will do it at a different rate than, say, the aluminum saddle. So I have seen applications where the copper tube actually rubs on the aluminum saddle itself and creates a pinging. The good news is it will stop when it hits steady state and warms up, but just be aware that that's one of the things that I've seen in the field. Something else to be aware of is because these panels are constructed in 4 inch, 5 inch, or 6 inch widths, you can see the actual extrusions themselves when they are put together. Now, every manufacturer does something a little bit different. Some are directional, some are not. But either way, it's something to be aware of when you're installing or when you're specifying these. That is something that you can see. I mentioned a little bit earlier about the U-bends and interconnects shipping loose. Again, I like to show these things because I like our designers to understand what they're actually getting in the field. So in this case, when you start having a 2-tube, 6-inch extrusion, you can really start adding the number of connections up very, very fast for the mechanical contractor to install and make those connections. Now, whether they're pro pressing them or they're soldering them, there's still a significant amount of work that needs to be done in the field if those items are shipped loose. Modular panels. Our industry defines a modular panel as really an aluminum pan that's broken up on four sides, as seen on the lower left, and then a copper tube fastened to the back side of it. Typically, they come in 2x2 and 2x4 only. What you'll notice here is that there is no activation, and I'm going to talk a little bit more about activation in a second. But what you're really looking at is the copper tube itself just to the back side of the cassette. There's no activation there. And again, I would only recommend using these for heating only applications. I really wouldn't recommend these for cooling. Traditionally, these are piped using soft copper or hard copper connections, whether again, they're pro pressed or sweated on. So access getting into them, dropping them out of the ceiling grid, wherever they may be in a bathroom, tends to be a little bit more limited. All right, so now let's get to the interesting stuff. If you were to come to us and say, we want to start talking about a radiant cooling application, that's when we're going to start looking at some of more of the, I'll say, applied product or engineered products. And this is where we start separating from that linear modular market. And this is really where we open up the doors to different installation types, different aesthetics, and we start having a conversation about sound. So whether you're going into a closed ceiling, meaning if this is going into like a lay-in grid or a tegular edge or gypsum hard lid ceiling, those options fall into that category because it's a closed ceiling, basically wall to wall, no free space around the panels themselves. You're not allowing for additional convection. Cloud or free hanging examples where you're open to structure. You can manufacture different panel sizes at this point, larger panel sizes because you're not tied to a hard lid, or you're not tied to a specific substructure at that point. And then the other option is the chilled sails, linear extrusion panels, linear extrusion panels with copper tubes on the back side. These tend to give off more convective factors than they do radiant. So you typically see a little higher performance out of these. All right, so I keep talking about activation and what is this activation and what does it mean? Well, the activation itself, depending on the manufacturer, depends on what type they use. Manufacturers will use aluminum extrusions on the backside of the panels or graphite, and some even use steel. But really, when I say activation, what the activation is the means or the activation on the side of the panel that gets the energy from the tube to the face of the panel. Because overall, the higher the average surface temperature, or lower, depending if we're talking about heating or cooling, is what drives your BTUs per square foot. So if you can get a higher or lower BTU per square foot or a surface temperature, you're going to get more performance out of the panel, and the panel is going to react faster when it heats up or cools down. So the activation is really what drives the capacity of the panel. Now, I know what a lot of people are thinking, and I get this a lot too, of, well, it's as simple, it's a piece of cassette and some copper tubing on the back. But I like to show this because there's more of it, there's more that goes into these panels than just that. Even looking at it down on the tube level, some manufacturers use just round tubes. Other manufacturers will actually use a D shape. So they take that tube, that copper tube, and they D shape it so you get more surface area across the face of the panel. Because again, it goes back to that comment I made earlier, the higher or lower the BTU, the higher or lower surface temperature is what drives your capacity on the panel. So if you can make that average surface temperature lower in cooling mode, you get more BTUs per square foot, and thus you end up using less panels, which is less installation cost. All right, as far as finishes, solid or perforated, you have both options with different types of perforations themselves. Solid or smooth panels I traditionally would see more in the healthcare facilities or hospitals. The perforated panels tend to be used in high occupancy areas, classrooms, office spaces, things of that nature. The panels are tested according to ASTM 423, which is your sound absorption data, which measures your NRC. That is the amount of sound that's absorbed into the panel, and then how much of thus is reflected back into the space. So the acousticians on the project are going to ask for this information, specifically if you're designing, say, an open collaborative office area or a classroom. And those are the areas that you would want to see a perforated panel, traditionally a little higher perforation pattern, somewhere between 18 and 20% free open area. And then, of course, you have your insulation on the back, and depending on what that noise requirement is or the NRC of the space, will determine whether you need insulation or you don't need insulation. Different types of color, or excuse me, different colors. A couple notes: just stay away from metallic colors. Metallic paint has a flake in it, which actually affects the emissivity, which is what drives the actual performance of the panel. So you want to stay away from that because that will reduce your thermal capacity. And then also stainless steel, it's very shiny, has a low emissivity. If you do need to do a stainless steel, you want to make sure that's a painted stainless steel, so you change that final surface finish. All right, panel dimensions. Standard panel dimensions, anywhere from 2x2 to a 2x10. These were pretty standard going out as far as lay-in grids, tegulars, things of that nature. Now, the comment I'll make about overall panel sizes, in order to reduce the cost overall, the install cost, I always recommend using larger panels. So if you can think of, instead of using 5 2x2s, because then you would have 5 of the panels, 5 times the handling cost, more hoses, and then also 5 hanging kits, you can get away with 1 2x10. It really, really lowers the install cost overall when you can use larger panels. So I would recommend that as you look at your designs. Non-standard panel sizes, all the way up to a 4-foot width and then a 12-foot in length. Now, the disclaimer I'm going to say on this is those are dependent, very dependent upon your substructure and the type of ceiling you're putting in these in. So generally, if you're going to lay a panel in a standard laying grid, tabular or standard 15/16 grid, you really don't want to go anything over, say, 30-inch width and 10 foot in length, because the deflection across the face of the panel as it heats up and cools down will start pulling up out of the grid and you'll see changes. It won't lay flat. But as you start getting into a open to structure application or free hanging cloud application, then you can start going into those larger widths and larger lengths because deflection isn't as predominant. You don't have a reference point, so you don't see it as much. Now, I also say non-standard panels because non-standard panels could be larger size, or they could be, say, a 21-inch by 7'6". So if you're going wall to wall and you need a exact dimension, that's also a non-standard panel and is available on the market as options. When we talk about activation on the backside of these panels, and we're going to talk a little bit more about this when we get into some of the integrated ceilings that I'm going to show you, but we have the opportunity and the ability, I should say, to change the piping on the backside of the panel, meaning we can change the meanders, we can change the tubing, the spacing to accommodate, say, a cutout for a linear light or fire suppression. In this case, here's an example of a 3.5 foot width panel by 8 foot length, perforated panel face with a cutout for fire suppression right in the center. You can see the insulation on the back. But what I want to point out is you can see the spacing here. We're able to, as an industry, to accommodate and change that spacing such that if you need to put fire suppression or AV or lighting or whatever it needs to be, we have that ability to do that. Now, one of the things I want to make mention about here is when designing a system, an overall space, what you want to try to do is minimize the number of variations on the job. So if you can standardize on a center location for fire suppression, same number of passes on same end, same panel size is repetitive over and over again, that's really what's going to help keep your overall cost down on the job, because the last thing you want to get or have the installer have is 50 or 60 or 70 unique panel types on the job that go in very specific locations. So if you can minimize those number of variations and repeat them over and over and over again, that will help with the overall install cost and install time. Piping configurations. I want to talk a little bit about this. So you have a couple different options. You have your same end connections, which again, pretty straightforward. Both connections, supply and return, are on one side of the panel. Opposite end connections, where you have them on opposite corners, or you also have the option to do opposite end connections with same side. Generally, most manufacturers will help you with, or as part of their package and scope, will do the shop drawings at the end. So they will actually maximize and work with the installing contractor to make sure that they're laying out the circuits within the room or zone in such a way that they're minimizing the number of variations using same end or opposite end connections. The other option that's out there is called split piping or 2x3 meanders. And this is where this is a single panel cassette, and it comes in different sizes, so it doesn't really matter. But there's actually 2 separate meanders in the same cassette. So there's 3 pass, 2 supplies, 2 returns. Now, where this is important and where this is an advantage to the installer is because if you have a chilled water line going down a corridor, you can utilize 2x3 meander pipes all the way down one side in a single circuit, use a same end connection, and then return on that same corridor or hallway. So it gives you some flexibility, and it also minimizes the in-room piping or in-room zone piping that's going to occur. So there's a cost savings in utilizing these kind of circuits. All right, I mentioned a little bit earlier, but connections. So panel to panel and supply and return, generally we utilize on these systems flexible hoses. They're they're oxygen barrier hoses, high rated pressure hoses. You can see your main header here coming off supply and return. There's a valve package here, and then it goes into your circuit and it's returned. The reason there's a couple reasons. A couple reasons we use these valve flexible hoses is one, access into the plenum. So here's an image of a torsion spring system where the flexible hoses are being used, and they're long enough and they're sized in such a way that it allows you to drop that entire panel out of the ceiling. Now, this is important because one, during installation, and then two, once the system's up and installed and operating, it allows the facility and maintenance engineers to get in there and not have to drop the entire loop out. So you don't have to drain the system, close it, isolate it, refill it. This allows you to get up into that plenum space, not have to worry about taking the hose off or draining that system. So it's flexibility and access into the plenum. You can see another panel down here with the activation. This hose hasn't actually been installed yet. So overall, reduces your install costs, give you some plenum access, and it also, at the end of the day, also helps with expansion and contraction, because those flexible hoses pick up that additional contraction, and it's not transmitted into the panel itself. The ceiling type and substructure will define how that panel drops out of the ceiling. So on the left is your standard tegular lay-in with gripple, and on the right is a C-channel hook-on system. So again, I just wanted to give you a little bit of point of reference of, depending on the substructure, it gives you an idea of how that panel would be accessed out of the plenum, out of the ceiling. So on the installation side, a couple notes here. So generally, when we install the panels, typically we'll see the installer install all the gripple or the gripple or the hanger kits first. So they'll go through, shoot the deck, and then they go back and install the panels. On the left, you can see the gripple hanger kits here. And in this case, this panel doesn't have any grid around it. This was a free hanging sail panel and then had an integrated fire suppression device in it. So there's nothing else going around that. In the picture on the right, the contractor installed all the hangers, all the kits, and then allowed Division 9 to come through, put all the grid installed, and then they can go in and put the active panels and inactive panels in later. The other thing I want to point out real quick is on this, the other option is when you run your supply and returns, the mechanical contractor run the supply and return, you can connect the supply and returns with the flexible hoses. So here's your supply. The hose is connected with a 12-inch, half-inch piece of copper, push-to-push connect fitting, close it, pressure test the loop, and then move on. And then once the active panels are installed, they can go back, take those hoses off, and then hook them up to the actual circuits themselves. So there's some flexibility there with the install too, depending on how the trays are going through. As far as on-site protection, things to be aware of, all the panels from all manufacturers will ship with some sort of film on them and protective gear, just because it is a finished product going in the ceiling. The other thing I'll also recommend in your specifications is some sort of crates or protection, especially if they're not going to be installed immediately. Over the years, I've experienced that these crates or boxes, depending on how they ship, they become workbenches or ladders for other trades going through. So if you could protect those panels, I definitely recommend it's worth the money. Now I just wanted to go through and give you a couple examples real quick of what these look like. Corporate headquarters, these were free hanging panels, device integration with inactive strips in the middle and the ceiling fans. Again, just a little bit more of an idea of what these things can look like installed, whether they're custom colors to match the structure themselves, and they have device and lighting integrated, larger size panels, 4x8s or 3.5x6s, integration with lights in between. So again, trying to minimize the number of panel variations. One of the things I mentioned, and I want to point out again, is you don't always have to go full blown all system, the whole room. It's always an option just to look at just the perimeter and do the perimeter heating and cooling on that side. You don't have to always incorporate all the panels into the interior core space. Gypsum and plasterboard, closed ceiling applications. These panels come with torsion springs and a slot. So all these panels in the hard lid are accessible and drop down, so you can always get back into the plenum space. Tegular edges, again, whether it's 9/16 or lay-in, this was a teaching hospital. We'll integrate, molding manufacturers will integrate into any ceiling type with any different type of edge. Chilled sails, these are the extruded sails, extrusions, linear. These were 4x8s, copper tubes on the back. Again, these have a little bit more of a convective output than they do radiation, but again, another option, just a different aesthetic. Healthcare facilities, these where we would see solid ones or solid panels along the perimeter, and then higher bay, higher applications, 2-story lay-in panels up on the ceiling on the diagonal there. So again, I just wanted to give you a little bit gist of what these systems can look like. Now, everything we've talked about is going to apply. I'm just going to take it literally a step further in what our industry calls either integrated metal ceilings or full metal ceilings. Now, the only difference between what we talked about thus far and this is instead of the manufacturer, the radiant manufacturer, just supplying the panel, the kits, and the hoses, hanger kits, and the hoses, now the manufacturer takes responsibility for everything, meaning the entire ceiling. So now we're doing the inactive, the active, the perimeter trim, the lighting integration, the cutouts, all of that gets incorporated into our scope. Now, I also know what a lot of you are thinking at this point, because you do cross over 2 trades. You cross over mechanical in 23 and also division 9. And I've seen it done a couple different ways on how the contracts have been broken up. I've seen it where mechanical carries just the active panels and the hookups, and then division 9 carries everything else and does all the installs, the grid, the trim, and the inactives. I've also seen where the mechanical carries everything, and then the division 9 contractor is a sub to 23. My recommendation is the latter, because typically you are not relying on 2 contractors to go through 2 coordination processes. You have a single point of contact, running point, and making sure that everything is right when it comes to all these things. Again, I mentioned it, different types of ways of installing a full metal ceiling, or I'll say integrated ceiling, depending on how you want to call it. But again, it makes, by doing this and having this supplied by a single manufacturer, you get consistency from a color point of view, and you also get consistency from a perforation point of view. So you don't want to mix and match and have, say, division 9 do all the inactive panels from a manufacturer and substructure, and then have the active panels done by somebody else, because you're going to get inconsistencies between the two. A couple different installations here. This was a torsion spring application, perforated panels, integration with the lights and tracks. This is a C-channel installation, where there's inactive service strips in between here, and then there's the cutouts for the lights, and these are all perforated 2x6 panels. These sit on the tracks themselves, so all these panels are removable and then hingeable down. Again, panels along the perimeter, when you're talking about these different types of unique rooms and non-square rooms, the panels along the perimeter are usually field cut, and these are going to be inactive 10 out of 10 times. We try to keep the consistency of the active panels on the interior core space. You really don't want to cut an active panel if you can prevent it. All right, so the last market here, and I'm going to just get through this real quick because we've got a couple minutes, is more of the industrial look. And these panels are meant to be a low-cost installation. Typically, they come in longer runs. You'll see these up to 20-foot strips, and they can go in combinations of a single panel strip all the way up into a 4-panel configuration. These go into typically larger bay production facilities, gyms, non-cooling applications, although the panels themselves can be used for cooling. But in applications like these are traditionally heating only. A lot of sports arenas, things of this nature that we typically see, warehouses, applications like this, because it's a lower cost installation. Production facilities, manufacturing, if you have an application where you are utilizing or designing a manufacturing or commercial space that has waste heat, it's a great application to recover your waste heat through water-to-water heat exchanger, or whatever it needs to be, or air-to-water heat exchanger, and then utilize that water through the panels themselves. It's a great way to save some energy. So, all right, so quick spec review, things that I want to just walk out of here with everybody, making sure they make note of this, is when you write your specs and look at jobs, make sure you're writing down the standards, the thermal performance, whether it's ASHRAE 138 or the EN standards, depending if it's heating or cooling. Make sure you're looking and working with the architect to specify the acoustical standard in the space, and that you guys are lockstep on both sides of that. Substructure, whether it's going into your lay-in grid with the hanger kits, or if you're talking a little bit more of the complexity and going into the metal ceiling, if you're going to be integrating with the architectural side, again, make sure you're coordinating with the architect to make sure you're both on the same page. And then access and piping, make sure you're noting what's being used to connect those. And then the other thing I want to make a mention of, depending on the project size, mock-ups. Mock-ups prior to release are extremely important, especially for larger project sizes when we're talking 20, 30, 40, 50,000 square foot of panel, to make sure that the integration's being done properly, the cutouts are being done properly, Division 9 is on the same page as Division 23 is, and then that gives a chance for the entire design team to sign off on everything, and everyone's happy with what they're getting. As far as, this is my last slide and my 2 seconds of a pitch for Zehnder, when it comes to us as a company, we will approach things a little bit different, because a lot of the times when you come to me or ask me for a cooling solution, I'm going to ask you what the space looks like, and then I'm going to give you options as far as what products or solutions fit into your space. But I want to know what your goal is and what the building goal is before I start recommending, because we have so many different solutions that what you come to me with may not be the best solution for it. So it's a very collaborative approach, and that's how we approach it. We have a team of dedicated, experienced rating professionals up at the factory in Buffalo. We also have project managers, depending on the project size, that will help manage that project throughout. They are responsible for the shop drawings and layouts. So we'll work with the installer to work on and you would actually get as the designer, shop drawings to sign off on, which would include the circuits, the loops, how the panels get connected, the overall GPM of the circuits, and then the performance. Lastly, we've got online selection software that incorporates all of our products. So that also includes the hydronics, which includes our fin tube, convectors, unit heaters, things of that nature, along with the ceiling panels. And then we have our global competency, which is over in Europe. We have support from them over there too, and they have, like I showed you a little bit earlier, years and years of experience with this. So if we can't answer it out of North America, we always have another reference at the competency center in Germany. So I want to thank everybody for their time. And Jim, I don't know if you've got any questions that you want to hop in with.
Yeah, there's 4 questions. I'll give people a second to type some other ones. Just quickly in summary, thank you for attending. There is a survey when you log off. We appreciate if you fill that out and help us out how we can serve you better. We will send out a final summary that's going to have a link to the recording. There's a summary of the questions and answers, and then we'll also resend the slide deck. And then let us know if you require PDH credits. And then lastly, we have upcoming 2 other webinars. The next one is Tuesday, April 26th. It's regarding HVAC design for warehouses and other large open spaces. And then lastly, before we break for the summer, we're going to have one on Tuesday, June 7th, and that will be technology updates for applied rooftop units. All right. So Mike, let me get into the questions. I know it's a little sometimes difficult to hear them versus reading them. The first one is, how is the 5-degree deadband required by code factored into the temperature points in the heating and cooling set points? This question was generated around your slide number 18 when you spoke about the ASHRAE standard number 55 regarding thermal comfort.
Yep, so generally on the heating side, we would design 68 degrees set point temperature on your heating, and then 75 or 78 depending on the cooling. So that would give you your 5-degree deadband.
Okay, great. And next are 2 sort of application questions. What are some typical concerns or pushback that you hear from owners / designers regarding objections to the first cost, ventilation requirements, maybe a lack of future flexibility, et cetera, like that? And how do you respond to those concerns?
Yeah, so over the years, this is actually a little longer of an answer here, but over the years, the initial feedback, I'll say 12 years ago with radiant cooling was, I didn't want to be the first one. It's going to rain in my building. It costs too much and the controls are too complicated. It was always the three C's, right, that I always heard. And over the years, because of the energy code, because of energy requirements, because of the way that you guys are designing your buildings and incorporating condensing low temperature systems into the spaces, it opened the doors up for more radiant applications. Now, there were a lot of radiant installations already out there, but we as an industry had to do a better job, and TC 6.5 has done a great job of that over the years too, of really highlighting them and bringing them to the forefront, because there were a number of examples out there and no one really realized that they were utilizing radiant cooling applications. So with regards to the controls, well, there's enough out there that we've gone through iterations of understanding how to simplify the overall controls, whether it's through a 6-way valve or a 3-way valve. It doesn't overcomplicate the points. I am a big proponent of keeping it simple. Put a standard set point temperature in the space, let it control your dew point, and then you're going to run a little higher or lower temperature like I talked about, but it's going to basically open a 2-way valve to the circuits themselves. That's been just some of the pushback. The biggest pushbacks I've seen over the years has been integrating and utilizing hoses, the flexible hoses. But again, now we're at a point in the industry where there's hundreds and hundreds of thousands of these things installed throughout, and maybe millions of millions globally. And the hose market's come such a long way that they're high temperature, high pressure, and the fittings themselves are generally not the issue when it comes to the connection. It's more of the hose itself.
Okay, great. Next is, what industries or applications do you see open to accepting this style of design? Some examples are, commercial retail or commercial offices, school/university, lab pharma, probably sports arenas, et cetera, like that. So he's looking to see where is this mostly applied?
I would say a lot of the installations, vertical market that's really latched onto it has been higher education universities, whether they're on the college level. Just in this area alone, I could name, 4 or 5 universities just in this area that utilize radiant cooling applications. And again, it goes back to the lack of maintenance, the comfort. I don't mean to simplify this, but it's almost like a set it and forget it kind of thing. So from a maintenance point of view, the facility engineers and the university love it because they're creating a more comfortable environment for their occupants. They're creating a quiet environment, and then it's really lack of maintenance when it comes to that. Before COVID, we did a lot of open collaborative office areas, tech on the West Coast, which has sort of dropped off the map ever since COVID. It kind of happened. There's still some going on, a lot of building owned or owner-based buildings where they own the systems over a long period have really latched on to the technology.
Okay, thank you. Next, it says, it looks like the operating temperatures can accommodate geothermal equipment. Is that correct?
Yes. Yeah. So the source, however the water temperature, the source that you're getting it there, from a radiant point of view, it doesn't affect me. But yes, geothermal, actually our facility up in Buffalo uses a horizontal geothermal loop underneath our parking lot to supply the chilled water and hot water to the panels.
Okay, next is are dew point sensors essential at each space or zone?
The answer is no, they're not. Now, when you take a look and try to figure out where to put those dew point sensors, my recommendation is always at the worst case scenario. So if it is a large open office, I would put them at a location where you're going to see the worst humidity. But you don't necessarily need one in every space because that'll drive up cost. Along perimeters, a lot of the times with non-operable office windows, I'll see a number of offices being ganged together on the same circuit in the same zone, two, three offices like that. That helps reduce cost too.
Okay, and then I'm going to switch onto the chat. because there's a question in a similar vein to that last one. How do you ensure that under all potential operating conditions, there will never be condensation on the radiant panels? Is there a technique to keep the chill water temperature below dew point, especially if users open windows or open doors or windows in humid outdoor conditions?
Yeah, so there are factors that you can build into your design to help minimize that event from occurring. Now, if it's an entry point into the building, traditionally I'll see a double door vestibule with a fan coil or some sort of latent device in between there to help pick up that slug of unconditioned air before entering the space. And then the panels can start right there, right outside that next door on the interior core. Panels are lightweight, they're fast reacting. So even if well, let me back up. If there are operable windows in the space, window switches or cutoff valve or cutoffs with regards to if the windows are opened, they'll close the valve. Now, those can get expensive depending on how many you have. But again, you would also have your humidity sensor in the space that if that failed, there are backup devices that you can put on the supply line of your chilled water loop. That is a mechanical device. It's almost like a wick where if condensation starts, and that's where it's going to start is at the coldest point because that's the coldest water temperature at that point, not the panel surface. Condensation starts to form, it wets the wick, and then it actually closes a two-way valve. So it's a mechanical backup to your control system. And then also if there's window switches and or a barrier between your entryways. So there are a couple different ways to approach that.
Okay, and I think we spoke the other day. So traditionally, you try to design your water temperature fairly low to your dew point, just because the lower you can get that chill water temperature, the little bit more capacity you get out of your your sensible cooling panels.
Correct, and there's been a number of studies. I know one engineer did a study on condensation for sensible and chill beams, but applies to this too. And I also know there's been some studies done out of Penn State. There's been a number of studies that actually show even when you cross that threshold and you force the panel into, I'll say, condensation mode, it takes a long time for condensation to actually form on the face of the panel, upwards of 8 hours, even when you cross over. So it's not an instantaneous thing that just happens immediately if you lose control of the building.
Okay, great. And then the last question has to do with radiant heating. It says for applications that are adjacent to windows, approximately how much radiative heat is lost through the window? And would it be more energy efficient to use baseboard heating and the traditional convective approach?
Well, it really depends on your heat loss of the facade, right? Because you develop your heat loss based on the perimeter load. And that's how you're going to size either the panel area or you're going to size, I'll say, the traditional convective approach baseboard. Both will solve our means of solving your problem. From a radiant point of view, what's really happening is that radiant effect is heating the surface of the glass. So you're actually creating a more comfortable environment for an occupant that would be standing next to that glass, and they wouldn't feel that level of discomfort. When comparing that to a convective, an all convective piece of equipment along the wall, thin tube, you're going to feel that hot air coming up across the glass. You're going to feel that cold air coming down. So it's a different sensation, but either way, the systems would be sized to handle the load of the perimeter.
Okay, great. And then the next question, probably, consider a like a kitchen or a conference room that has a very dense or large cooling load per square foot. So are there rules of thumb or guidelines to forecast where the cooling load is too dense for appropriate radiant panel cooling surface temperatures? Is there a square foot per ton or a BTU per square foot value that you really can't achieve with radiant cooling panels?
That's a really good question. So Generally, if it's going to be, let's say, an office area and you're talking about a conference room, generally there's only so much ceiling space that a radiant panel could take up. And those are traditionally a perforated metal ceiling or active ceiling integrated with standard ACT tiles. Traditionally, I would say call it somewhere between 30 and 35 BTUs per square foot of active panels. That would be giving you your performance for the radiant side. But traditionally, what I'll end up seeing in those areas that have either a dense population or really high load for whatever reason it may be, is using another technology in combination with the panels, whether it's a sensible only chilled beam because you're using the same water temperatures, or I've even seen where you can't have or don't have the excess air from the air handler, utilizing a passive chill beam. So there's other options that you can integrate into the radiant system that works collaboratively with that radiant water temperature. So there's different options.
Okay, yeah, that's similar, kind of in fashion to a chill beam system, that you're just limited in your ceiling space on how much, cooling you can fit in there. So, okay,
Right.
That looks like that is all the questions. Let's just stay on for a minute or two, see if anything else pops up. Buck, I see that you're on. Do you want to, chime in with the thank you or anything?
Oh, yes. Thank you, everybody. Again, we know your time is precious, and we appreciate you giving us a little bit more than an hour of your day. And we hope you find that these webinars we put on are useful. And again, we thank you for attending.